Okay, for number 28, we are going to balance a redox reaction. Woo! And so to start, we're going to assign the oxidation numbers. And so you can see I've done that here. And where there are oxygens, I assign a -2. So here in this chromate ion, or dichromate ion, we have -14 from those oxygens. So the two chromiums would have to contribute a total of 12. So each one is +6. Oops. And then for the HNO2, assigned a +1 to the hydrogen, -2 to the oxygen, and figured out that the nitrogen would need to be +3. The Cr3 plus is just going to be +3. Then I assigned -2 to the oxygens in that final molecule to find out that the nitrogen was +5. And so what we're going to use are the top numbers for the individual atoms to look at how things are changing. So we can see that the chromium is going from +6 to +3. And so I'm going to say each chromium must have gained 3 electrons. And so this is going to be our reduction. And we can see the nitrogen changed. And each nitrogen is going to lose 2 electrons. So this is going to be oxidation. Okay, so now we can split into our half reactions. We'll have Cr2O7 minus becoming Cr3 plus. And then we'll have our HNO2 becoming NO2 minus. Or I'm sorry, NO3 minus. Okay, so let's start with the chromium half reaction. On the reactant side, we have 2 chromiums. And on the product side, we only have 1. So we need to balance that by putting a 2 here. And so from up here with our change in oxidation numbers, we said each chromium is going to gain 3 electrons. And we have 2 chromiums in our reaction, so there will be a total of 6 electrons gained. And so now we need to account for the difference in the number of oxygens. So I'm going to add 7 waters to the right to match the 7 waters on the left. Or I'm sorry, the 7 oxygens on the left. But now I need to account for the hydrogens that I've added in, so I'm going to add 14 protons. And so to see if this looks good, I can make sure that the charges are the same on the left side of the reaction and on the right side. So here I have +14 minus 6 for 8, minus 1 for +7. Oh, this is 2 minus, okay. So if we're +6, and then on the right here we're +6. So our charges match on both sides. And then we can move on to the second reaction. So the number of nitrogens are the same on the bottom. And we know each nitrogen is going to lose 2 electrons from the oxidation numbers. So we just have 1, so we'll lose 2 electrons. So I need to take care of my oxygens by adding a water to the left side. And now, of course, I have 3 hydrogens on the left and 0 on the right, so I'll add 3 protons here. And I can see that I'm neutral on the left and I'm -3, +3 on the right, so I'm neutral. So the charges are the same for both of those. Okay, So my next step now is to add the two equations together. But when I do that, I need the number of electrons to cancel. And right now I have 6 and 2 electrons. So to make the number the same, I'm going to multiply this bottom reaction by 3. And so now that the number of electrons are the same, I can go ahead and combine my two reactions. Okay, so now that the reactions have been combined, I have this overall, but I need to cancel some things that are the same on both sides. So I'm going to cancel these 3 waters out and say that I have 4 waters left on the product side. And then I'm going to have those 9 waters cancel out, and I'll have those 9 protons cancel, and I'll have 5 protons left on the left. And so my new overall will become, and so then I can see that I would have 4 waters in my final equation. And this is balanced in acidic conditions, and you can see that because we have these excess protons in the reaction. In number 29, we have this titration curve. And from it, they want to figure out the pKb of ammonia, which we know is a weak base. And so when we look at this titration curve, there's a few points of note. So one is point C here. That's going to be our equivalence point. And we can see it took 5 milliliters for us to get to the equivalence point. And then our pH is below 7, which makes sense because we have a weak base and a strong acid being combined. But so then at 5 milliliters, which is our half equivalence point, and corresponding to point A, what we'll have is our pKa value. And you can see that it's in the middle of this sort of flat region, which we would call our buffer zone. And this makes sense because when we work with buffers and use the Henderson-Hasselbalch equation, we use pKa plus the log of base over acid. But so then if you walk over and kind of estimate then what the pKa is, it's a little greater than 9. So let's call that like 9.2. So we can say pKa is about 9.2. And we know that pKw is equal to pKa plus pKb. So 14 minus that pKa of 9.2 will give us about our pKb, which with my estimate would make our value come out to be about 4.8 for the pKb. And then the correct answer is C, which is pretty close to what I've gotten. And number 30, we're mixing some strong acid with another strong acid. And we're trying to figure out the pOH of that solution. And so we know that the HCl is basically going to be donating its own source of H plus ions. And so if we can figure out the mole of those H plus ions, and then add that to the moles of HNO3's protons, we can combine those to get our total moles of protons in the solution, and then divide that by our total volume. And once we have that number, then we can get pH, because that will be our concentration of protons. And so, to get the moles of these, I'm going to do moles is equal to molarity times liters. So for the HCl, I will have 0.05 moles. And so that would give me 0.05 moles of protons also, because we have a strong acid. It's going to completely dissociate 1 to 1. And then for the HNO3, I'll have 0.25 moles. So that would be 0.25 moles of the protons from that source. So my total moles of protons will be 0.3. My total liters will be combining that 500 mils with the other 500 mils for one total liter. And so I'm just going to have 0.3 molar protons. When I take the negative log of that, I should get pH. We'll find that pH is equal to like 0.5229, which is the same as answer choice B. It makes sense that it's super acidic because we're mixing two strong acids together. In question 31, we have platinum decaying to gold. And we know these nuclear decays are always first order. And we have this combined first order equation here to work with. They tell us the half-life and ask us to figure out how much platinum would remain after 72 hours. So our time is going to be 72 hours. And that matches our units on half-life, so that's good. And what they want us to figure out is how much, what fraction of platinum would be left. And so what they're really asking us for then is what is NT over N0. So we can go ahead and just say the natural log of that NT over N0 is going to be equal to negative 0.693 times the 72 hours that have passed, divided by our half-life of 19.9 hours. And when we evaluate that, we get that the natural log of our NT over N0 is equal to negative 2.51. So then we can do e to the power of both sides to cancel the natural log, and we get that this ratio is equal to 0.0815, which is the same as 8.15-ish%. Which corresponds to answer choice E. For number 13, we want to figure out which species is the best oxidizing agent, or which species is the best at getting reduced. So we're going to look on the reactant side of our data sheet and look at for these things being reduced. And so if we would want to look for copper being reduced, we'd have to see copper becoming something like copper minus, because it would be gaining an electron. And that's not going to happen. This is a transition metal, it'll become positive. So that's not going to get reduced. And then the same thing is kind of true for this F minus. So if F minus gained another electron, it would become F2 minus. And we'd have to go into a whole extra shell in order to fit another electron on fluorine. And so this isn't going to happen either. And you won't find those reactions on the data sheet either. But we do know that manganese can gain 2 electrons to become solid manganese. And it does that with a potential of negative 1.18 volts. Hydrogen peroxide, in the presence of protons, can gain 2 electrons to make water. And it does that with a potential positive 1.776 volts. And cobalt can gain 2 electrons to form solid cobalt. Does that with a potential of negative 0.277 volts. And so the one that will be the best oxidizing agent, or the best at getting reduced, will be the one with the most positive potential, and that will be answer choice C. So here we have this redox reaction, and they want us to figure out how much work can be done if the battery is reading 1.3 volts. So this 1.3 volts is going to be our E cell. And we know that when we're talking about work, what we're really referring to is delta G. And we can convert between delta G and E with this delta G equals negative NFE equation, where F is just Faraday's constant. So what we're going to have to figure out is how many electrons are transferred in the reaction so we can figure out N. So I've gone through and assigned oxidation numbers, and we can see that zinc is changing from 0 to +2. So we have that zinc oxidation. And we can see that the manganese is changing from +4 to +3. So we have that reduction, where it would have to gain 1 electron to go from the +4 manganese to the +3 manganese. And so we could go through and do the entire balancing thing with the waters and the oxygens and the hydrogens. But all we need to do is figure out what our N value is. And so we know eventually, despite how many waters or protons there are, we need to make sure that the electrons cancel out. And so we would have to multiply this bottom reaction by 2 to make that possible. And so then we would say that the N is just equal to 2. And if you want some practice with balancing, you could do all of the balancing and make sure you end up with this equation. Okay, but then we can say delta G is equal to negative 2 moles of electrons times Faraday's constant, just coulombs per mole of electrons, times our E cell, which they gave us as 1.3 volts. And when you solve this, the number pops out in joules. You get negative 250,861 joules per mole. And so this is going to be the same as negative about 251 kilojoules per mole. And so the negative sign is saying that the reaction can do the work on the surroundings, and then the 251 kilojoules is how much of that it would do. For number 34, you can figure out the molar solubility of AgI in an aqueous solution of 0.1 molar NaI. And they give us the KSP, so I've written out the KSP expression here. And we know that the value will correspond concentration of Ag plus times I minus. And so the molar solubility that we're looking for is really going to be like the X from the ice table. So we can go ahead and set up our ice table. ICE. And we're going to disregard the solid. And so now we have to think about what this sodium iodide is doing. So they don't give us a KSP, so we can assume it's a strong electrolyte completely dissociating, as most sodium things are. And it's giving us sodium ions and iodide ions then. The sodium isn't present in our equilibrium, but the iodide is. So what this is doing is it's giving us some initial concentration of iodide. And there's nowhere else that the silver is coming from, so that'll have a 0 for its initial value. We'll have plus 1x for both of them. And we can set up our KSP expression then. We can say 8.3 times 10 to the negative 17 is equal to x times 0.1 plus x. And so this k is really small. And so we can say that any added or subtracted x's can be ignored. And so our expression then is just 0.1 times x is equal to this value. And so x is just going to be equal to 8.3 times 10 to the negative 16th molar. And that'll be our molar solubility.